everyone, and welcome to the Environmental Science and Engineering Podcast channel. On this channel, we address water, wastewater, solid waste, and environmental management systems of countries and cities around the world. And we also cover fundamental topics related to environmental engineering. We are environmental engineers. As researchers involved in academia and the scientific world, we aim to convey scientific knowledge to you in a more understandable language in a podcast format. While preparing these episodes, we utilized academic articles, scientific books, official websites, and reports, and we also share our own field and research experiences. Transforming science communication into a format that everyone can understand is very important for us, because environmental engineering is no longer just a technical field, it is a discipline at the center of societal sustainability. Don't forget to follow us on our Spotify, YouTube, and Instagram accounts and like our episodes. Let's move on to today's topic. In this episode, we will talk about the design of water treatment plants. We will discuss what a water treatment plant is, what processes it involves, the steps followed in the design process, and the basic principles that must be considered in design. This is actually a broad field that even 500-page textbooks can only explain in detail. We will try to present this episode to you in general terms and in plain language. However, we will create part-by-part episodes in the water treatment series, and this will be part 1. In part 1, or this episode, we will give general information about water treatment plant design, while in part 2, we will talk about water treatment processes such as aeration, coagulation, flocculation, sedimentation, filtration, and disinfection. So, let's start. First of all, I welcome our expert guest and start with our first question. Before moving on to water treatment plant design, I think we first need to clarify this. What is the most important starting point when designing a facility? That is, where do engineers start when they decide to build a water treatment plant?
Thank you. It's good to be here. That is a very pertinent question. The first step in water treatment plant design is to properly analyze the characteristics of the city where the facility will be built. This is because every city has a different population, geographical structure, water source, and climate conditions. Therefore, the capacity and design of a plant are determined based on these factors. Especially population information is a critical data point here. Without knowing the population, the amount of water the plant needs to treat daily, which is the flow rate Q, cannot be calculated accurately.
So we first need to know the city's population so that we can estimate how much water that city will need in the future.
Exactly. Engineers use different population projection methods to make this estimation. These include different mathematical approaches such as the arithmetic increase method, the geometric increase method, the logarithmic increase method, and the decreasing rate of increase method. Generally, the population data for the last 15, 20, or 30 years of the city is examined, and based on this, forecasts for the next 30 to 50 years are made. This is because a water treatment plant is not a short-term investment. It is usually planned to have a lifespan of 30 to 50 years.
So it's not actually completed in the single stage. As the population increases, the plant's capacity is also expanded.
Absolutely. We call this staged design. For example, when a water treatment plant with a 30 years lifespan is designed, it is usually done in 2 or 3 stages. Let's say the city's population will increase from 100,000 to 150,000 in the first 15 years. In this case, new reactors, tanks, or filters are added in the second stage. If the population reaches 200,000 after 30 years, the plant capacity is doubled. This means that expansion areas are left on site beforehand so that new units can easily be added.
So, does the population only increase over time, or do periodic changes also affect this calculation?
Yes, that's a very good point. The population can fluctuate not only over the years, but also seasonally. Especially in tourist regions, the population can increase several times during the summer months. This is a very noticeable situation in cities with intense summer tourism, like Antalya. Similarly, in winter tourism regions, such as ski resorts, the population increases during the winter months. Additionally, in agricultural regions, seasonal workers can increase the local population during certain periods. So, these seasonal fluctuations must be taken into account when designing the plant.
I'd like to delve a little deeper now. After determining the population, it is necessary to calculate the plant's capacity, which is the flow rate. At this point, the per capita water consumption is a very important criterion, isn't it?
Absolutely. One of the most critical parameters when calculating the flow rate is the daily per capita water consumption amount. This is directly related to how much water the plant needs to treat daily. However, this value varies in every country and even every city. Generally, water consumption is higher in developed countries because the standard of living, hygiene habits, and areas of water use are more extensive. For example, in the United States, daily per capita water consumption can be as high as 300 liters. In contrast, in African countries, this value can drop to around 50 liters. In Turkey, the average is around 200 liters per day.
So we can say that not only the infrastructure, but also people's water usage habits directly affect the plant's capacity.
That is absolutely correct. The use of water-saving facets, communities with high water consciousness, the level of education, and the lifestyle in the city greatly affect consumption. For instance, in places where there is high awareness of water conservation, people take short showers and don't leave taps running unnecessarily. However, in regions where water is abundant or awareness is low, behaviors like long shower times and hand washing increase water consumption. Nevertheless, household water consumption alone is not sufficient. Industrial water consumption in a city must also be taken into account. Institutions such as factories, production facilities, hospitals, schools, hotels, and slaughterhouses use a significant portion of the water. The water needs for such facilities are generally calculated using average values taken from the literature. For example, in an area involved in animal husbandry, the daily water consumption amounts for cattle and small livestock are determined separately.
So a city is not just made up of residences. Even the industry, tourism, or healthcare sectors in that city affect total water consumption.
Exactly. And to this, we add a special type of flow rate called the fire flow rate. The fire flow rate is the amount of ready water that must flow from fire hydrants in case of emergencies. This value can vary from country to country and even from city to city. For example, in Turkey, the average fire flow rate is taken as 20 liters per second. However, different fire flow rate values may be set in different parts of the world. In higher risk areas, such as industrial facilities or chemical warehouses, this value can go up to 50 liters per second. In lower risk areas, 10 liters per second may be sufficient.
So far, we have talked about the importance of factors like population, per capita water consumption, industrial use, and fire flow rate in water treatment plant design. But there is also a topic that is often overlooked, the loss leakage flow rate. Could you elaborate on this concept?
Of course, you have touched upon a very important point. The loss leakage flow rate refers to the portion of the produced or treated water that is lost in the network during distribution. That is, the plant treats the water, but some of this water can be lost in the pipes, connection points, or meters before it reaches the city. This covers both technical losses, for example, leaking pipes, and administrative losses, for example, incorrect meter readings or unauthorized water use.
So even if the water is treated, it's not always equal to the amount of water coming out of the tap. There is a difference in between.
Absolutely. Especially in old infrastructures, this rate can increase significantly due to the wear and tear of pipes, loosening of joints, or poor material quality. The loss leakage rate can go up to 50%. This means half of the produced water can be lost within the system before reaching the citizen. In addition, administrative issues like incorrect meter readings or unauthorized water use also cause this rate to rise.
That is quite a high rate. Is the situation similar in developed countries, or is the difference significant?
There are serious differences. The average loss leakage rate in European Union countries is around 23%. According to research conducted in the U.S., about 19.5% of the treated water is either unbilled or lost in the distribution system. In China, the average is around 20%, but in well-managed cities, this rate can drop below 10%, while in smaller cities, it can go up to 30 or 40%. Generally, rates of 10 to 25% in developed countries and 30 to 50% or even higher in development countries are considered normal.
So, in cities with good infrastructure, this rate can drop below 10%.
Exactly. If the pipeline is modern, the connections are robust, the meters are accurately calibrated, and the network is regularly checked, the loss leakage rate can be reduced to even below 5%. However, this requires both infrastructure investment and effective management. Because leaking pipes, old treatment facilities, or inadequate water storage systems cause a significant amount of water to be wasted. This is not only a technical problem, but also an economic loss.
So far, we have discussed how to calculate the capacity of a water treatment plant and which factors the flow rate depends on. Now, how do we decide where to establish this facility? In other words, if a treatment plant is to be built for a city, what are the criteria for site selection?
This is one of the most critical stages in water treatment plant design, because poor site selection can significantly increase both construction costs and operating expenses. First and foremost, the facility must be close to the water source. This source could be a dam, lake, river, or groundwater. Being close to the water source reduces both transmission costs and prevents the deterioration of water quality during transport.
So, the shorter the distance between the water source and the facility, the more advantageous it is both economically and technically.
Absolutely. Furthermore, the topography of the city is also very important. Water treatment plants are generally located at high elevations of the city. The reason for this is that the treated water can be distributed to the city by gravity flow, meaning without the need for pumping. This reduces energy consumption. Conversely, wastewater treatment plants are usually built at the city's low elevations, closer to the discharge areas, such as a river or the sea. The slope rate of the land is also a very important criterion. A slope between 2 and 5% is generally considered suitable. Construction difficulties and the risk of erosion increase in steeper areas. Additionally, the soil must have a high bearing capacity and be resistant to settlement. If the groundwater level is too high, it can also pose problems for excavation and foundation work.
Are environmental factors such as earthquakes and wind direction also taken into account?
Yes, absolutely. Environmental factors such as earthquake risk and distance from fault lines, wind direction, and distance to residential areas must be considered. The facility should be established away from residential areas due to the use of chemicals and noise. Furthermore, easy access to road, electricity, and communication infrastructure must be available for the facility. Factors such as future population growth, urbanization direction, and expropriation costs are also considered when planning the facility. If possible, public lands are even preferred. This both reduces costs and provides room for expansion. Finally, let me add this. The location of a water treatment plant should be at a point where the water will be transported with the least energy and which is economically sustainable in the long term. This is because pumping systems are very costly in terms of energy, and correct positioning can reduce a large part of the operating expenses.
So, in summary, the location of a water treatment plant is not just a technical, but also a strategic decision. It must ensure that the water is transported at the lowest cost, and it must secure environmental and economic sustainability in the long term. So far, we have discussed how the flow rate is calculated when determining the capacity of a water treatment plant and where the facility should be established. However, when designing a plant, not only the quantity but also the quality of the water is just as important. In other words, we know how much water we will treat, but the question that needs to be asked now is, what kind of water will we treat?
Absolutely. One of the most critical stages in the design of a water treatment plant is the thorough analysis of the raw water quality. This is because the processes we will use, the chemicals we will choose, and even the size of the tanks change according to the water quality. Generally, drinking water treatment plants draw water from surface water sources, that is, from rivers, lakes, or dams. Although these waters are not as polluted as wastewater, they still need to be evaluated in terms of some physical, chemical, and microbiological parameters.
And what are these parameters generally?
First, we look at the amount of organic matter. This is usually measured by the total organic carbon parameter. In addition, the ions in the water, namely components such as chloride, sodium, calcium, magnesium, sulfate, and nitrate, are analyzed. This is because these ions affect both the taste and the corrosive properties of the water. Another important group is heavy metals. The presence of elements such as copper, zinc, iron, manganese, arsenic, lead, cadmium, and mercury is definitely tested. High concentrations of these substances are dangerous for both human health and the infrastructure.
So it is not possible to determine the appropriate treatment process without knowing the chemical content of the water.
Exactly. Furthermore, the pH value of the water, i.e., whether it is acidic or basic, is also very important. Drinking water should generally be in the pH range of 6.5 to 8.5. In addition, the hardness of the water is checked. Hardness is caused by dissolved calcium and magnesium ions in the water. Very hard water causes scaling in pipes. Very soft water, however, can corrode metal surfaces. Another important parameter is turbidity. This is caused by suspended solids in the water, and its unit is NTU, nephelometric turbidity unit. Globally, it is generally desired that it be below 1 NTU for drinking water.
So, clear water is actually a quality indicator, not only visually, but also technically.
Exactly. In addition, the color, odor, and taste of the water are also evaluated. Color is measured in platinum cobalt units and generally needs to be below 15 units. The water must be colorless, odorless, and palatable. Furthermore, substances such as pesticides, polychlorinated biphenyls, DDT, or trihalomethanes that may have carcinogenic effects should not be present in the water. Finally, one of the most important parameters microbiologically is fecal coliform bacteria. These bacteria should not be present in drinking water at all. This is because these bacteria indicate fecal contamination and thus the risk of disease.
So, in summary, it is not enough for water to merely look clear or clean. Truly potable water must be safe both chemically and microbiologically. This is only possible with correct analysis and appropriate treatment processes. So far, we have discussed the site selection, flow rate calculations, and the analysis of raw water quality for a water treatment plant. But after all this information, we come to perhaps the most fundamental question. How do we treat the water? That is, what processes are applied in drinking water treatment plants, and how are these processes designed according to which standards?
This is truly an important point because every country has set its own drinking water quality standards. However, when we look at them, generally there are great similarities among these standards. For example, the World Health Organization sets international reference values. The EPA in the USA implements these standards at the national level. The European Union has its drinking water directive, and in Turkey, the regulation on water intended for human consumption is applied. These standards define the limits within which the physical, chemical, and microbiological parameters of the water must fall.
So, we can say that the basic criteria for safe drinking water are almost the same no matter which country you go to.
Exactly. Now, when it comes to the treatment processes, a drinking water treatment plant usually starts with an aeration unit. In this unit, dissolved gases in the water, such as carbon dioxide, are removed. The oxygen level of the water is increased, and the oxidation of some metals is facilitated. Some facilities have an ozonation unit after this stage. Since ozone is a very strong oxidant, it not only provides disinfection, but can also remove organic matter, iron, manganese, and even pesticides and micropollutants from the water. Then, coagulation, flocculation, and sedimentation units usually follow. In these units, small suspended particles in the water are aggregated with the help of chemicals and then settled and removed from the water. This process is very effective in removing turbidity and color-causing substances from the water. The next step is usually filtration. The most common system is the rapid sand filter. These filters both operate with high efficiency and take up less space. However, in some regions, slow sand filtration is also preferred. In slow filters, both physical filtration and biological treatment occur together. This method is especially applied in facilities with large areas and in rural areas. After filtration, the most critical stage is disinfection. Chlorination is usually performed at this stage. Chlorine is a disinfectant that is both inexpensive and leaves a residual effect throughout the network. This means that a small amount of chlorine remains in the water even while it's being transported through the pipes, and this prevents bacteria from multiplying again. That is why chlorination is still the most widely used disinfection method in the world. However, UV disinfection has also become quite common in recent years. Especially in decentralized systems or more modern facilities, microorganisms are made inactive by breaking down their DNA with ultraviolet rays. When used together with chlorination, it forms a highly effective combination.
Are more advanced technologies also used besides the systems you mentioned?
Yes, of course. Today, membrane technologies, namely microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, are also becoming increasingly common in drinking water treatment. These methods are preferred especially in regions where the water needs to be treated to a very high quality or where the source water is highly turbid or salty. We already have a separate podcast episode on membrane technologies regarding this topic. Our listeners can find the details of this subject there.
Great. So, in summary, every water treatment plant combines different processes according to the water quality, land conditions, and standards of the region it is located in. Classic methods are used in some places, while more modern technologies are used in others. Well, we have thus come to the end of the first part of our discussion on the design of drinking water treatment plants. Today we talked about how the site for water treatment plants is selected, how flow rate calculations are performed, and why the quality of the raw water is so important. You have shared really valuable information. Thank you.
Thank you. It was a very enjoyable conversation.
In the next episode, which is part 2, we will delve into the details of the processes used in water treatment plants. We will discuss step by step which pollutants are removed by which processes, how these processes are designed, and what needs to be considered. Thank you for listening to us. Don't forget to subscribe to our channel, like our episodes, and turn on notifications to be informed about new episodes. See you in the next episode.